Long before humanity ever studied the stars, mathematics began in the dirt as a matter of practical survival. Imagine living thousands of years ago in a settlement along the banks of the Saraswati River. Every morning, you send your cattle into the dense forest to graze. Without words for numbers or a written language, you have no way to verify that every animal has returned by evening. To solve this, you might place one pebble in a clay pot for every cow that leaves in the morning. When they return, you remove one pebble for every cow that enters the settlement. If the pot is empty at sunset, your wealth is accounted for. This method uses a concept called one-to-one correspondence, the direct physical matching of one object to another. This systematic act of matching pebbles to livestock provided the origin for the natural numbers 1, 2, 3, and 4. The earliest physical evidence of this tracking takes us to the Lubumbo Mountains in Africa. Here, archaeologists found a bone featuring 29 uniform, deliberate notches dating back 35,000 years. Human tracking became more sophisticated over the next 15 millennia, as seen on the Ishango bone found near the headwaters of the Nile. This ledger contains specific asymmetrical groupings, 11, 13, 17, and 19. These are the prime numbers between 10 and 20. These carvings indicate that humans were isolating complex numerical patterns tens of thousands of years before the development of written language. Eventually, the counting system reached a limit. If a farmer had 5 apples and gave all 5 away, early mathematics had no way to represent the resulting state. There was only a void. The solution emerged from Indian philosophical traditions. The concept of shunyata, or emptiness, was treated as an active state achieved through meditation, perfect stillness, not a mere lack of objects. This philosophical concept transitioned into mathematics in the Bakshali manuscript. The text uses a bold dot, called a bindu, as a physical placeholder for that emptiness. In 628 CE, the mathematician Brahmagupta formally operationalized this dot. He defined zero mathematically as the result of subtracting any number from itself. By establishing strict arithmetic laws for zero, Indian mathematicians created a conceptual framework that allowed for a complete representation of quantity. Brahmagupta then addressed the next logical problem, the result of subtracting a larger number from a smaller one, such as 3 minus 5. He grounded his answer in the commercial reality of the Indus Valley. In trade centers like Lothal, merchants needed to balance assets against liabilities. Brahmagupta defined positive numbers as dana, or fortunes, and negative numbers as rena, or debts. This commercial logic expands the number line to the left. It moves past zero into a mirror dimension of negative values. This model clarifies why multiplying two negatives results in a positive. If a creditor removes 4 of your debts, you are effectively richer. The combination of positive numbers, 0, and their negative counterparts formed the category we now call the integers. As societies complexified, measuring became as important as counting. A farmer dividing a single field among 3 heirs could no longer rely on whole integers to describe the shares. Fractions were formalized to represent these parts of a whole, allowing one integer to be divided by another. Zooming into the space between 0 and 1 reveals an infinite progression. When we introduce fractions, the gaps between whole integers are filled with values like 1/2, 1/4, and 1/8. Combining all integers and fractions creates the set of rational numbers, providing humanity with a tool for measuring reality with infinite precision. This infinite number line represents the culmination of thousands of years of human inquiry. The line serves as a physical record of human progress. It contains the herder's pebbles, the meditator's stillness at 0, and the merchant's ledger. Humanity invented these rules as a series of brilliant tools to navigate, trade, and define our place in the universe.